Alrighty, let's go ahead and get started with the last video on area between the curves. Um, the only reason why this one might not be optional is the fact that there's a little bit of, with respect to y area. It should not freak us out. That's why I've been constantly talking about the more positive one being the above one with respect to x. I called it the more positive one oftentimes because it's the more positive one minus the less positive one, or the more negative one. That remains the same when I start looking at it with respect to y. And let's go ahead and look at this. These are with respect to y, and they represent those two curves right there. Okay, this one right here that starts in the lower left is the y cubed plus 1. That right there is y cubed plus 1. This other one right here is the 1 plus 4y minus y cubed. Now notice that there are two areas. There's this area right here, which is in the first quadrant, and this area right here, which sort of overlaps the third and the fourth quadrant. Let's concentrate on this one over here. Let's try and figure out what the limits of integration are. And we're going to figure that out in the same way. But notice that when we're doing this, okay, and we have, if you have something with respect to y, and it's something like this, and then something like that, you are going to be dealing with cross sections that run this way now, okay? And it is going to be dy that is going to be your differential. So let's go ahead and find whether these intersect at nice, neat points, or whether we're going to have to be a little bit more creative. The ones obviously cancel out. This becomes 2y cubed minus 4y is equal to 0. You can factor out the 2y, and you're left with 2y and y squared minus 2. Now this is not the difference between two squares, because 2 is not a square, but you can force factor it, basically treating it or making it behave as though it is. And that winds up being y plus root 2 and y minus root 2, showing that their points of intersection are going to be at negative root 2, 0, and root 2. Now let's go back to the graph and actually visually see that. Here we have negative root 2. And this, remember, we're thinking with respect to y. Negative root 2 would be negative 1.414, and that is approximately where it is right here on the y-axis. Right here they cross at the x-axis where y is equal to 0. And here they cross where y is equal to root 2, just shy of 1.5, or what we should estimate as 1.414. Now, let's just concentrate on this area that is in the first quadrant. If I want to actually deal with that, okay, I'm going to have to figure out which one is more positive. Now, when we're dealing with integrating with respect to x, with the dx, more positive is up, okay? But when we're dealing with dy and we're dealing with expressions in terms of y, we need to talk about more positive in terms of x, okay? What is more positive in terms of x? And the reason we want to do it in terms of x is these expressions equal x. So which, on this interval, which x is greater? Which x is more positive? Just like on the x intervals, which y was more positive? Well, with respect to x, positive is not up, positive is to the right. So when we're dealing with this, the question is, which one on 0 to root 2, which one is farther to the right? And the answer is the negative cubic, the 1 plus 4y minus y cubed, okay? And so what we need to do here in order to get that small, that first quadrant area is 0 to root 2, and then it's 1 plus 4y minus y cubed plus 1, and that would be it, okay? Now, we're just going to go ahead and do that portion of it. The other portion would behave roughly the same, except for the roles have switched, right? And I'll go ahead and show you that one, and you can integrate it on your own since it's a polynomial. So we'll go negative root 2 to 0, and just the roles of those particular equations are swapped, because on the other interval, on this interval, negative root 2 to 0, this one is more positive. This one is farther to the right. Okay, and of course you can confirm it numerically if you can't get your mind around the graphical representation. You can go, okay, well, representative point between 0 and root 2 is 1. If I plug in 1 into here, I get 1 plus 4 minus 1, or 4. I plug 1 into here and I get 2. 4 versus 2. This one's larger. Well, let's go and plug in a negative 1 into here. Okay, plug a negative 1 into y cubed plus 1. You're going to get 0. Plug a negative 1 into here, and you're going to get 1 minus 4 plus 1, or negative 2. This one is more negative. This one right here is more positive, and that's why the difference has flipped. So you can think about it graphically, or you can think about it numerically, either way. But this is how you would set up the area between those two curves. Now, it just so happens that there actually is symmetry here. If you were actually to shift both of those graphs to the left by 1 unit, you would see the symmetry just a little bit better. And we can go ahead and do that. Let's go ahead and shift both of them to the right. And we can go ahead and now see that symmetry. Okay, and that symmetry right there means that this area is going to be the same as this area. So all I have to do is find the area of 1 and actually double it. Okay, so doing it with respect to y, not really that big of a deal. You just have to think about it in terms of more positive being to the right instead of more positive being up. Okay. Well, let's go ahead and let's move on to another problem, which is probably going to be a little bit nastier. Let's go ahead and move on to, okay, and this one's a fun one. I actually once tutored a guy from Kincaid where his teacher loved problems like this, just loved them. And I think it's because, I mean, these are kind of neat problems. They do require you to have perhaps a little bit more robust, problem-solving skills. Now, let's go ahead and take those and let's put them into Grapher real quick. Let's go ahead and go y is equal to, and that winds up being x, and then x plus 3. Let's go ahead and change this one. That winds up being 4 divided by y is equal to 4 divided by x squared. And then, of course, let's go ahead and add a third one, and that is going to be x minus x squared divided by 4. Okay, and what we really are looking at is this interval, this area right here, okay, in this first quadrant. Now, here's the thing. I have 3 equations. That is kind of a bizarre looking area right there. And what I need to do is I need to figure out how to break it up. Okay. Well, let's find those points of intersection. Okay. Let's go ahead and just make ourselves a little bit of a rough sketch of that particular scenario. We know that we have this that comes up right here, and that's x squared plus 3x, so that's f of x right there, okay? Because here is the 0 at 0, and the 0 at negative 3 is going to be, out over here. We know that we have 4 over x squared, and so that's going to kind of run like this, and that's going to be 4 over x squared, so that is going to be g of x. And then we have this negative, this right here is h of x. Okay, so we have 3 points of intersection that we need to find. Now that is of course an abysmal graph, but just hang with me. Okay, this right here is g of x. Okay, and it has the 4 over x squared shape, right? I mean, you recognize that as basically the square of a reciprocal function. Okay, well let's go ahead and find this point of intersection. Now, this point of intersection between f and h is obvious, okay? Both of them have a factor of x. That right there is 0, 0. We don't need to go fishing for that one. But let's go ahead and find the intersection between f and g. So f and g intersection. I know that I'm going to do x squared plus 3x is equal to 4 over x squared. Okay. Now, this winds up being x to the 4th plus 3x cubed minus 4 is equal to 0. Now, can we actually find a good solution to that? You could actually, instead of doing this, you could actually fiddle with it just a little bit. I'm actually gonna, let's go ahead and see if we can guess what it is instead of having to actually deal with it. That kind of looks like 2, 1, okay? So let's go ahead and see whether 2, 1 is actually going to, oh, actually we're looking for this one up here. This one looks like 1, 4. So we're looking for between f and h, I mean f and g. So we're looking for this one right here, and it looks like it's 1, 4. Is it? Well, let's try that ordered pair with both equations. So we're going to go ahead and plug 1 into here, and we're going to get 4. We're going to go ahead and plug 1 into here, and we're going to go ahead and we're going to get 4. So it actually is 1, 4. So we're just going to use sort of guess and check. This actually looks like 2, 1. The question is it? We'll go ahead and plug in 2 into here, and we get an output of 1. Go ahead and plug 2 into here, and we're going to get an output of 1. So we do indeed have those 3 points. Here's the thing. If I'm going to be integrating and getting cross sections that are with respect to dx, something changes right here as I'm progressing through this interval. Something changes right here. From 0 to 1, I have f over h. From 1 to 2, I have g over h. So I need to be very careful that I set these up accurately, okay? So I know that from 0 to 1, I'm going to have f, which is x squared plus 3x, minus h, which is x minus x squared over 4 dx, right? Now, and of course, let's go ahead and make sure that we see that. Okay, so from 0 to 1, I see the fact that it's this curve, which is f, over this curve, which is h. So f minus h. From 1 to 2, I have g over h, and that winds up being 4 over x squared minus x squared over 4, and let's just put that like that. Now, I'm not gonna take time to actually do the integration there. The hard part is what's called the partitioning of the area. And you just have to be able to sort of see in your mind's eye these cross sections as they're accumulating across this area with respect to dx. And as a result of you doing it this way, you can at some point find where the relationship changes with respect to those cross sections. What kind of cross sections are you actually going to have from 0 to 1, and are they different from 1 to 2? And in this case, the answer is yes. Now, like I said, I'm not gonna integrate this because that would actually take way too much time. Let's go ahead and walk through, at the very least, one more example. And it's kind of the same variety, so I want to go ahead and get the grapher back up. Let's go ahead and call it negative x cubed. Let's go ahead and do this one as square root of x, and let's do this one as 3y plus 7x minus 10 is equal to 0. And if we go ahead and look at all three of those together, we see this area right here, okay? And we see the fact that the same way it was in the last one, the relationship changes midway through the interval. I mean, not exactly midway, but in the midst of the interval, as you're trying to accumulate cross sections, you wind up with a bit of a problem. Okay, let me go ahead and try to recreate at least that to some extent here. Okay, and this is going to look horrible, but you're going to get the idea, okay? This is the y is equal to negative x cubed. This right here is the linear, which was 3y plus 7x minus 10 is equal to 0. This right here is the y is equal to the square root of x. Now, here's the thing. This right here is one function. This right here is another function. That's the negative x cubed, okay? And this right here, this linear, is a third function. Now, on this interval right here, from this point of intersection to the axis, I have green minus red. But on this interval right here, I have green minus blue. So I'm going to have to set up two separate intervals in order to actually find this particular area. Well, the first thing I have to do is I have to find the limits of integration. Well, limits of integration really aren't that hard. I mean, I could go ahead and do it analytically. I'll just go ahead and let you know that this over here is -2, and this right here is 1. Yeah, not drawn to scale. So if we have that, we know that we're going to set this up, and like I said, I'm just going to set this up since we're kind of running out of time. -2 to 0. I'm going to have green. And of course, I'm going to have to solve this for y. So 3y is equal to -7x plus 10, or y is equal to -7/3 x plus 10/3. So when I set this up, I know that it's going to be -7/3 x plus 10/3 minus a negative x cubed. Now, it's obnoxious because of those fractions, but it really, it's burdensome, but it's not difficult, okay? The second integral over the second interval is going to be that same obnoxious fractional linear minus root x. And if I actually plop those into my calculator, or if I do it by hand, either way, I'm going to wind up with the area. But like the previous one, the whole magic of it had to do with the partitioning and recognizing the relationship between the three functions that are given. That does it for 6.1, the area between curves. We're going to go and move on in the next set of videos to volumes of revolution, and that ought to be just tons of fun, so look forward to that.